Okay, let's get going here. So today we will talk about test number 2. We will continue with cluster analysis, and we will start a discussion on project number 2. Again, regarding save our stats, I don't know if you haven't taken a look at this website. I'm the one who actually constructed it, and if you want to know more about what is all happening, I recommend going down to the timeline, and you can see, for example, stuff that's happening this week. Well, you can see what happened on Saturday. There was a rally outside the student union before the football game. In fact, you will see me holding up a sign if you watch any of the news media coverage that was given. But on Tuesday, the University of Nebraska Executive Graduate Council meets to discuss the proposed elimination of the graduate programs. So previously, the UNL Graduate Council, which I'm an elected member of, we voted 10-0 against the elimination of all these programs. We have communicated this to the University of Nebraska Executive Graduate Council, which oversees graduate education at all campuses at the University of Nebraska system, and they meet on Tuesday to decide whether or not to eliminate programs. On Wednesday, there's going to be an interesting press conference hosted by the UNL chapter of the AAUP, which stands for American Association of University Professors. They've had some people come in to examine the actual financial health of the university, and it sounds like they've come up with some conflicting findings from what UNL administrators have said. So there's a press conference. It's going to be on Zoom if you want to watch it. Something else I wanted to mention is that, and maybe I even said this in class, is that last Friday, we were expecting the report from the Academic Planning Committee to be released regarding what they thought of the Chancellor's proposal to eliminate all these departments. Well, the report has been done and has been forwarded to the Chancellor, but it has not been made public yet. And I haven't seen it. No one's seen it other than the Chancellor's team. So we were all expecting to have the report made public on that date, but it didn't happen. So what we understand what the next step is, the Chancellor will be reading the report and making a decision on his final proposal. And once that is released, then the report will be actually released as well. We have no idea when that report will be given, but obviously it needs to be done by December 5th when the Board of Regents meet. So that's where we are at with regarding that issue. I needed to buy a new webcam for my research, and so I decided to try it out here today in class. This is the first time I've recorded in 4K, so if you end up watching any of the videos, hopefully it will be a better view of me teaching. Are there any questions before we get going here? Okay, so let's talk about test number 2. First of all, the overall grades. I posted that to Canvas. The Stat 494 grades were interesting. In terms of the mean was 77%. The median was 88%. Both are measures of centrality that you will learn about in your very first SAT course. So what can cause the mean to be so much lower than the median? Yeah, unfortunately, there was lots of low grades. Well, I don't necessarily want to say lots of low grades. There were some very low grades that really weighted down, caused that mean to go down. So those of you who've had a mathematical statistics class, you've definitely heard of skewness. There is an extreme, the distribution of grades were extremely left skewed, to put it in a statistical sense. 97 was a very popular grade. These students were not missing the same problems. It just so happens 97 was a popular grade. It was a high grade for both 494, SET 494, and also for 873. take a look at the standard deviation, and that's also, says that there was a lot of variability as well. Now, note that there are still a few students who have to take the exam. They will be given for a variety of different reasons why they didn't take it already, and they will be given a different version of it. So this test is 20% of your grade. And, I understand there's probably a few of you, or some of you, I should say, who are probably not satisfied with your overall grade that you got on the exam. Well, 20% is a significant part of your grade, but then again, that means there's 80% of your grade that's based upon other stuff in this course. And so if you're in a situation where, I really didn't like that grade that I got on the exam, similar to what I said in the discussion board post, do what's often referred to as a what-if analysis. Meaning that, okay, I know what this grade was. What if I, let's say, got 100% on everything else in the course? What would be my final grade? What if I got a 90% on everything else in the course? What would be my final grade? Do that. Based upon that, then you should be able to make a decision about, okay, what should I do in this course? Should I continue on? Should I try to study harder? Or should perhaps even drop? You're welcome to come talk to me as well about this. But the first thing I will ask you is, did you do a what-if analysis? At least try. If you're unsure how to do it, I will help you. But at least try to do that first. Okay? So just as a reminder, when I grade, I use Word's tracked changes tool to put my grading comments in the exam. And so you should see something like this where, nice big red font, underline. Though that's how my track changes should appear to you. If by chance instead you just have simple markup on versus all markup, you can see it's a lot harder to see. So I strongly recommend that you have all markup on so that you can fully see my comments. Now there were some, I would say probably about 5 students in class who decided to put their answers in the tests in their own red font, which then makes it a little bit difficult for you to see my comments. In those instances, I tried to change my track changes to a blue font so that you could still see it. But I would appreciate it in the future, and I didn't say this before, don't use a red font for your answers. You can use a different color font, and that is obviously helpful, but don't use red. Okay, let me get back here. Please make sure that you include your code and output for every calculation that you make. I did start taking off points if I didn't see it. Usually I only did it the very first time. But again, this is for your benefit. So there were some times where students did not include all their code and output, and I couldn't figure out what they did wrong. And I had to take off full points in because sometimes I can understand what's going on, but a lot of times I can't if I don't see your code and your output. Please always include that. I will take off more points in the future if it's not there. So let's talk about some specific problems on the test. This is not meant to be critical, but rather to help you learn about how to do this better. Some of these comments that I make here, I track these comments. I put it in a file on my computer called potential final exam questions. So please take note of this. On 2A, I didn't take off points for this. I want to bring it up. Sorry, I went past it. So 2A was meant to be a simple problem. Why is the correlation matrix more appropriate to use with this data than the covariance matrix when performing a PCA? What I was hoping to see students do, and some did, but most did not, and that was talk about there's a different amount of variation amongst the variables. That's what I was looking for an answer. So actually calculate an estimated covariance matrix. And you can see, if you look at the diagonal elements of this covariance matrix, wow, there's a lot of differences. That's why we would prefer a correlation matrix. Now, what ended up happening is that many students focused on this statement that I made here. Do not assume the measurement units for each of the numerical variables are the same. They could be actually the same. In fact, they were. But I didn't want you to assume that, because I didn't want that to factor into your answer about should I use a covariance matrix or correlation matrix. But a lot of students were saying, well, the units are different, so therefore I must use a correlation matrix. I didn't take off points, though. But I wanted to give you some background on that, because I often would comment on the exams about this issue. 2C was one of the more frequently missed problems. I was kind of surprised about this. And in 2C, you needed to actually write out formally what the principal component was. State the first principal component for this data. Make sure to use the correct notation. Okay. One thing that was often missed was putting, I know it's looked kind of small there, but that is an asterisk on the Y. There was a difference between just Y itself and Y star or Y asterisk in the notes. Without the asterisk means you're working with a covariance matrix. Also, what I was looking for in this problem was something that said that you were dealing with standardized variables. That's very important, because if you gave this equation to someone and not put that part right there, they might be thinking, oh, okay, I'm just going to put in the regular old variable values. So you need to say it was standardized. A common mistake that I was finding students make as well was that they were just simply giving me the principal component scores. The scores are the actual calculated values from applying the first principal component equation to the data. I wasn't looking for that. I was looking for the first principal component, the actual equation. So because of that, then there was points taken off for it. Okay, number 3. Come back to it. I really like this problem. I think this is the first time I've ever asked a cluster analysis question like this. And I needed to do it like this because obviously we hadn't gotten that far in cluster analysis. And the key with this problem was, tell me how you can measure the distance, or what could also be referred to as the similarity, between these two clusters relative to one of the 4 different methods. So nearest neighbor is the easiest. All I need to do is say, okay, if I'm going to measure the distance between these two clusters, I'm measuring the Euclidean distance between these two observations. That's it. That's all I was looking for. Then when we go to furthest neighbor, then it becomes this. I'm measuring the distance between those two. That's all I was looking for. Sometimes students were going through the whole process about how would I actually implement nearest neighbor? How would I actually implement furthest neighbor? That's not what I was looking for here. I was looking for how would we measure the distance or the similarity between these two clusters. So, be careful. Make sure you read the question fully. You can always, of course, ask questions to me during the exam if something's not clear. I know, obviously, during the exam, you're maybe more rushed, and that you can misinterpret. Also, something to be very careful about here. So when I introduce furthest neighbor cluster analysis in class, I said the number one problem that students often have with this method is they will say, the way I decide to join two clusters is to look for the distance that is the furthest between the clusters. So let's say so again, students were misunderstanding stuff, and they say, suppose I have, let's say 10 different clusters. How do I decide which cluster to join in the next step? Well, I always look for the furthest distance between clusters. That's not correct. Rather, how we measure distance between clusters is to look at each observation in, let's say, cluster 1 and cluster 2, find the furthest distance between those observations in those clusters, and then that becomes the distance. In the end, you're still always looking for the smallest distance between clusters to decide which clusters to join. Some students also were not fully getting centroid. They were saying, well, I'm going to look at the center of both clusters, find the distance. That's how I'm going to measure. Well, there's different definitions of center. You know, in your first stat course, you learn different measures of centrality: mean, median, mode. You needed to say what is the exact measurement that we're looking for in terms of the center of a cluster. For centroid, it's the mean. So that's what I was looking for. Now, going into the exam, I thought 4B would be the most missed question. It was kind of high up there. Perhaps the principal component question that I mentioned before was the most missed. So when constructing a scatter plot of scores for two principal components, it's important for the x and y axes to be the same numerical range and the plot to be square. Why? And the key word I was looking for, or key phrase, each principal component has a different amount of variability. And so if you change, let's say the x-axis to be, let's say, between -5 and 5, and the y-axis to be between -1 and 1, that will distort your perception of understanding differences between the observations that are displayed by the principal component scores. And so fully take into account that, and what we normally put on the y-axis would be principal component number 2. To fully take into account then the variability differences explained by both principal components, you need to put everything on the same range of terms of your axes, and then also to make sure that the plot is square. And then lastly here for part D, the key word I was looking for was conditioning. That's how you are able to get in different or more variables on a trellis plot by conditioning on particular values of certain variables. Okay. So I hope that's helpful, that additional explanation of what I saw in the test. Were there any questions regarding the test in terms of how to do any problems or anything related to it? If you have a question about why I took off a certain number of points on your test, just talk to me individually about that after class. Okay, why don't we move on then? So we're going to come back to cluster analysis here. We're going to talk now about the goblet example. So we have these agglomerative methods, and there's 4 of them. We're going to look at applying one particular agglomerative method to the goblet data. I believe it was nearest neighbor. Yes. So here's our measurements for our goblets. And, an ultimate goal for these archaeologists who were doing this, let's say this dig, was to come up with a way to classify these goblets. Beforehand, there was no particular way. And so the end analysis that would be actually done will be the cluster analysis here. We've done this grouping kind of informally with principal component analysis. this nearest neighbor clustering method will allow us to do it now formally. So, the steps then in the process. Number one, get standardized data. You could, for this particular data set, use non-standardized data. We talked about that a little bit before. We're just in this class right now going to only look at the standardized data. And we're just also going to only focus on nearest neighbor, just because we don't have time to go through all the different methods. So we find first the standardized data. We find the distances between each pair of observations. And then we apply nearest neighbor as the method to do the cluster analysis. So to get the standardized values, we use the scale function. To get the distances, we use the dist function. To actually do the nearest neighbor clustering method, we use H+. H stands for hierarchical. This is a hierarchical clustering method. Notice what we put in here for the argument D, all these distances. And then for a method, we say single. That stands for single linkage, which is just another name for nearest neighbor. Okay. Now, we put the results into clus.nn for the lack of a better name. In R's terminology, this is actually a list format for an object. Inside the list, there are a number of different components. One component is called merge, which tells you which observations were joined at every single step of the clustering process. Then height then corresponds to what was the standardized Euclidean, let me restate that. What was the distance between the observations or the clusters when they were joined? If it is just simply observations, that would be standardized Euclidean distance. If it's like a cluster that has a few observations in it, joined with another cluster, well, then we have to think about, okay, well, with nearest neighbor, we look at the two observations that are the closest to one another in each cluster, and then we find the standardized Euclidean distance. Okay, so the very first thing that was joined, or very first, every observation starts in its own cluster. And what we see here is observation 3 and 16 were joined together in a cluster. Previously, with some of the simpler examples that we looked to see, did that make sense? We could actually visualize in a plot what was that standardized Euclidean distance. And we saw, oh yeah, those are pretty close to one another. That makes sense why they were joined. Here we have essentially 5 variables that we're looking at. And so we can't just simply look at a plot, a 5-dimensional scatter plot, to make that judgment. But what we can do in a similar manner is look at the principal component scores. So this is from the PCA notes. Let's find observations 3 and 16. Right there. Now, the first 2 principal component scores do not give us 100% of the information in the data. So we have to be careful now interpreting this. But we do know that 2 principal component scores gave us a significant proportion of the information that was explained in the data. Notice how close 3 and 16 are. Okay, that makes sense then why these 2 observations were joined together first. They appear very close to one another. Any questions about that? Okay, let's keep on going. Let's see here. So next was 6 and 14. So let's find 6 and 14. Let's see, right here. 6 and 14. Again, close. Next was 1 in 15. That's kind of interesting. 13 wasn't involved. So again, remember, these two principal components don't show us all the information in the data. Let's look at what happens if we include a third principal component. So again, 3 and 16 were joined first. Look at how, though, that third principal component, which is, this is a bubble plot, how those bubbles are very similar in size. So if we were actually looking at a 3D scatter plot, we would expect 3 and 16 to be still very close to one another in that third dimension, right? Next, look at 14 and 16. Again, bubbles are similar in size. Next was 1 and 15. You can see 13 there too. Notice how 1 and 15 have a similar size bubble, but 13 does not. It is actually a little bit smaller. That's why 13 wasn't joined to 15 or even 1, and that 1 and 15 were joined together first. Because there is a larger distance that we don't see in just 2 dimensions. That third dimension helps us to see it. Let's see if, do I have a plot here? What were the 1 and 15? Sorry, now I'm going a little bit different from what I planned. 1 and 15, and we skipped 13. Do we see it on here? There's 1. So let me see if I can quickly get the 3D plot up. I should have done that beforehand. I'm sorry. Hopefully I get this right by just going in the middle of my program and start highlighting stuff. Okay, let's find 1 and 15. So I think 1 and 15, the labels are, if you see where my mouse is, are just above that plane, where the points are actually right below the plane. So then we're looking for 13. Am I missing 13? Okay, I see it. 13 is, I think, right here where you see my mouse. So there's where you see the difference. That's why 1 and 15 were together, were joined together. So next then, 19 is joined to cluster 2. That is when we had 6 and 14 joined. This is the last one that we'll do like this. So 6 and 14 were joined together, and look at, there's 19. Again, look at how those bubbles are very similar in size. So what I recommend that you do is walk through this process yourself a little bit more. Maybe even take some of these other clustering methods. I should say maybe. Do with these other clustering methods exactly what I just did here, and see if you can make sense about how things were actually joined together relative to these principal component score plots. It's just as helpful to understand fully what is going on to make intuitive sense for why certain things are joined together. So now let's look at a hierarchical tree diagram, or what R labels as a cluster dendrogram. Remember that 3 and 16 were joined together first. And what was the height? 0.401. 0.401. Right there. Okay. Next was 6 and 14. So that has a height of 0.45. Sorry. And you can keep on, comparing this to that data frame that was printed that shows the whole ordering of what's being done. Now, the purpose here to look at one of these tree diagrams is to decide where to what's called cut the tree. Meaning, where do we stop the hierarchical clustering process, because this process goes all the way until you have one cluster, and you don't want to have just one cluster. That kind of defeats the purpose of what you're doing. We are looking for differences between the clusters to an extent where each cluster is somewhat different from the other ones. And the way to make that determination from looking at one of these tree diagrams is to start looking for places where the distance between successive clusters being formed, that distance is, let's say, different or much greater than what we have just been encountering in the past. And so what I did here was I actually drew with the AB line function using a certain height, you could say, where I could cut the tree. So this very first one corresponds to 1.75. Why did I draw it there? Is because it looked to me that this distance between successive clustering, and it appears that this would be the previous one. Note that I would also look at that as well, even though it's not on the same branch. But it looks like this was put together, and then this was put together. I can see that that distance is such that that looks a little bit different from what we've been seeing. So I decided, okay, let's see what would happen if I cut the tree there. How many clusters would I have? 3. How do I know that? I look at the number of times that we intersect the tree. Now, another place where I thought would be reasonable to cut the tree was right here at about 1.45. I mean, I could have drawn it at like 1.44, 1.43. It doesn't matter. I'm just trying to get a line such that it's cutting the tree between successive joinings. How many clusters would I have here? Well, note that parts of the branches don't go all the way down, so I would still include this, and this. So that means I have 6 different clusters. And this is probably, I don't know if this is really needed. I did draw another line there as well. And that's going to result in, I think I probably have it written. Let me just look at that. 8 clusters. So these are possibilities. So once I have that, then what I like to do is use some of the tools, some of the graphical tools that we've looked at previously in this course to make a judgment about, do these clusters make sense? Are these observations similar to one another? If they're not similar to one another, then that maybe tells me, well, maybe I shouldn't have cut the tree at that particular spot. So I'm looking to see, do these clusters make sense? So just, I think we talked about this before. There's a function called rect.hclust, which allows you to actually put on your hierarchical tree diagram rectangles, that's what the rect stands for, corresponding to the number of clusters that you select. So if I did 6, and if I want the border to be red, then that's how we kind of show which observations are in which cluster. So we've looked at a variety of different ways to graph multivariate data. For example, a parallel coordinates plot. I could graph my variables on a parallel coordinates plot, color the lines corresponding to the cluster each observation falls in. Looking at that plot, I can make a judgment about, well, does it make sense? Are these observations different? Are these observations similar to one another? Another tool that we're going to first look at, though, is to do principal components. Get the scores, plot then the scores, colorize the plotting points corresponding to the cluster that a particular observation falls in. To help you with this process, I have written a function called pca.ca.plot. I'm not going to go over the function in class. I want you to go walk through every single line of the function to make sure you understand it. It's basically using tools that we've seen before. But I just kind of put them all together into one convenient function for you. To use this function, let me highlight some of this code here. Here's the function itself. It's in my goblet ca.r program. Note that the very last line is invisible in the function. And what does the last line of a function do? It returns the results. If you use the invisible function, nothing's returned. So if you haven't ever seen that before, which I bet a lot of you haven't, that's why I have invisible there. The reason why I do that is because I'm only doing this principal component thing so I can see plots. So I don't need anything returned. You can change the function if you want. That's fine. But what I'm going to do here is implement the function or run the function. The first argument is data.set for your data. So I put my data in here. Then I put in an object that contains the clustering results from using hclus. And so we save those results as clus.nn. Then I have another argument, num.clus, for the number of clusters I want to examine, in this case 3. A title for my plots, label equal true, meaning just label stuff. Note that this does use the correlation matrix. So if I run this code, you can see a whole bunch of plots just appeared. Okay, let me jump back over to my notes, and this is what we get. Let me make this a little bit bigger. Okay, so first we're going to look at 2 principal components. Excuse me. So 3 clusters. Here's one cluster. Here's another cluster. And there's another cluster. I know that by looking at the plotting symbols. Okay? Does this make sense for the clusters? Yeah. I can see why 24 and 23 are separated. I can see why 4, 5, and 17 are separated from the rest. You know, we have this 18 here. You know, what did we do with it? But, you know, based upon what I see here, it seems kind of makes sense. But let's look at a third principal component too. So what I've done here, excuse me, here's 24 and 23, 4, 5, and 17. Here's the rest. Remember the bubbles, that third principal component score, we have to adjust it so everything's positive. But one thing that I did here that's maybe a little bit different is if you have a red circle, that corresponds to a principal component score for the third principal component that is positive. For a blue circle, that corresponds to a principal component score, again, unadjusted, for number 3, that is negative. Okay? Look at how, it was questionable. Where should 18 go? But look at now the difference between 18 and this 4, 5, and 17. 18 is red. That's why it went with this set of observations versus the 4, 5, and 17. That's why. So now this is a little bit more reasonable. We have a little bit more justification for why 18 went where it did. We can look at the 3D plot as well. I'm going to just rotate this so that you can see it. Look at 4, 5, and 17. That's kind of in front of us here. Look at how 18 is quite different from 4, 5, and 17. It's kind of similar to what we see for those black ones, the other black ones. Now, yes, we do have some black ones down there as well. Perhaps, I don't know, maybe we need a fourth cluster? I don't know. Look at how 23 and 24 really stand out from the rest too. So overall, I'm not dissatisfied with what I see for these results. It seems like there's justification for it. So would I be comfortable with it? Yeah. I still, if I was to approach this on my own, let's say outside the class, I was given this data set, I would still try some of the other clustering methods to see what would happen. Would I get results that are maybe more justifiable or make more sense? I don't know how I could. I mean, still, I'm kind of interested in this 18 and some of the other black ones. But I'm pretty much okay with what I see. I still would want to do more. What about 6 clusters? This is what we get. There's that 4, 5, and 17 again. Look at how 18 is all by itself, as is 23, as is 24. And then I have this weird cluster. Let's go back to the tree diagram. There we go. So when we had, let me do some erasing too here. Oh, I still had that problem with erasing. Let's see here. Now, why? Okay, so I erased a little bit here. Remember how we saw 23 and 24 were separate. Remember how we saw 18 was separate. Typically, you want to avoid a situation where a cluster has only one observation in it. When I see that, then that makes me worried about using 6 clusters. Remember 2, how that stuck out? Look at where 2 was in this tree diagram as well. Let's go back. Here we go. So when I see something like this makes me worried. It would be hard for me to justify that indeed that this is a good place to stop the clustering process because we have all these observations which are quite separated from, they're only in their own little cluster. And so because of that, I would most likely say, no, don't do that. Don't use 6. You can see a little bit more in terms of when we have that third dimension that's involved too. Look at how where 2 falls into play. Note that the coloring of those, and perhaps, sorry, I didn't say this before, the coloring of the observation numbers corresponds to the actual cluster that it belongs to. Sorry, I didn't say that before when I did that plot there. So there are no plotting, different symbols like a triangle or a plus sign or a circle. Rather, just the observation number is what's plotted, and I colorize it corresponding to its cluster. Sorry again that I didn't bring that up. And this is what this all looks like in 3 dimensions too. So what do you think of 6 clusters? Well, I've basically already said it, but let's say how I actually worded it in the notes. I do not think this is desirable. Okay. Any questions? Comments? Yes. Well, if only 2 PCs should be considered, then that takes, and you could still do that, the bubble plot and the 3D plot, as long as you have more than 2 variables to begin with. So you can still do that, but just ignore those other plots. But if you feel as though that 2 PCs are enough, only focus on the 2 PCs plot. Okay. Other questions? Okay, we've already talked about that comment. Here's an interesting comment. So my function allows you to look up to 3 principal components. But there will be situations out there where 3 principal components are just not enough. So what can you do? You can still examine those plots that we just saw, but you always have to have in the back of your head, like, okay, I might be missing some useful information that I need to be careful with interpreting what I see in those plots, because it's not giving me sufficient information perhaps about my data. Now, what I would do though in this kind of a situation where more than 3 principal components were needed is I would do other plotting techniques as well. So we could do a parallel coordinates plot of the regular data itself. Or there are situations where, let's say you have 20 variables. Looking at even a principal component plot with 20 variables might be somewhat difficult. But let's say that 5 principal component scores were enough. 5 principal components were enough. Get those 5 principal component scores and do a parallel coordinates plot of those 5 principal component scores. That will be a lot easier than looking at, let's say, if you did have 20 variables, all 20 variables in one of these plots. Look at the parallel coordinates plots, and from that make a judgment. Does it make sense how these clusters were actually formed? So here's an example of using a principal component score. Using a parallel coordinate plot with the original data itself. Not with the scores, but just with the original data itself. And I used 3 clusters here. Based upon this plot, does it make sense why 3 clusters seems to be okay? Well, look at this. Look at the red ones. So this would be that, 4, 5, and 17. Look at how 4, 5, and 17 distinguish themselves in comparison to all the other observations. Look at how, what were the green ones? So 23 and 24, thank you. Notice how the green ones are somewhat similar to the reds, except once you get to W4 and W5. That's why they were distinguished in that principal component score plot. That's why they were different, what we see there. And so, based upon what I see in this parallel coordinate plot, yes, it makes sense for these clusters to be formed in this manner. These observations in each cluster have some distinguishing qualities to them. Oh, sorry, I guess I forgot this. I walked through my notes last night, and I guess I forgot that I did the principal component score plot too. And you see something similar. I would be careful with looking at 4 and 5 because we saw 2 or 3 principal components were needed. Don't put too much weight in 4 and 5 then. But we can see for component 2 and 3, look at how the green ones stick out. For component 1, look at how the red ones stick out. This is how you can justify your clusters. So after the clusters are found, then, one can try to interpret the clusters, what they represent in the context of the problem. This is something you should always try to do. So cluster number 1, which was represented in black. This has smaller PC number 1 values, indicating it represents the smaller goblets relative to the overall height. Let's look at some of these other ones. They're a little bit easier. Actually, cluster number 3, the green, has large PC number 2 values, indicating its top is larger than most when contrasted to its base. How about we just look at the original ones? So W4, W5, and W6 were base measurements. W1, W2 were the top of the goblet. And so we can see how these goblets have a big base, a big top relative to the base. The red ones have large tops as well. I'm actually visualizing a goblet here, so I hope you are doing that too as I'm using my hands. They have a big top and also a big base. So it's all about the base, essentially, here. Okay. Yeah.
When you're explaining these things, can you
Yeah, sorry.
Yeah. When you are saying cluster 1 has a smaller PC1 values and cluster 2 has a large PC1 values, so by this I understand that you should be looking at the principal components parallel coordinates graph, not the W's one. But while you were explaining this, you referred to the W's one.
Yeah, when I did this in the notes, I was focusing on the principal component one. When I actually vocalized it here, I focused on the other one. Both will be acceptable. If I had, well, maybe I will in the future. If I had to do this again, I probably would focus on the one with the original variables because it's a little bit easier to see. But it's good to have this here because oftentimes this is where you're at because you have so many variables. You have to use the principal component one. Any other questions? So on your own, take a look at some of the highlights here of using just regular old Euclidean distance rather than standardized Euclidean distance. Look at how I approached it, okay? Let's see here. I've been debating over the last few years just to take this out, and I haven't taken it out yet. There are other methods to determine the number of clusters. I think these are more older methods. I don't really see people use these much anymore. When I first started teaching multivariate, a course like this 20 years ago, I would teach this. I'll just leave this here for you if you are interested in this. It's just a different approach. It uses something called a pseudo-Hotelling t-square statistic, which basically is, let's say, a multivariate version of a t-test. And you can read it if you're interested. Okay. So let's now take a look at the project. So I'm going to flip on over here to the project. There are 3 problems in the project. Let me actually go back to my original document that we started off here. So this is going to be due tentatively. I have a feeling I'm going to have to move it. Tentatively, it's going to be Thursday, November 13th at 5 p.m. So a little bit over 2 weeks. Work in groups. You're welcome to change groups if you would like to. But if you do that, make sure you tell your other group members, both your former group and your new group, and let me know as well. But hopefully you can stay with the current group that you're with. There are 3 problems on the project. 2 are dealing with cluster analysis. The 3rd problem deals with something called discriminant analysis, which is what we do next after this section of the course. You now have enough background to do problem number 1. So for this particular problem, you're working with that NFL Combine data once again. And we're just basically going to apply one of these cluster analysis methods that we've talked about. This time it's going to be furthest neighbor. Use again only the numerical variables in the data set. Exclude the overall grade variable. So what this means is the first 4 columns in the original data set you're not going to use. Standardize the data before your analysis. Now, typically, you would not apply cluster analysis to this data set. Why do you think? Yeah. So with this data set, we already have ways to group the players based upon their position. So because of that, you would typically not use cluster analysis for this kind of a data set. Why are we using it then? First, it's convenient because we've already been using this data set. But a second reason is for an instructional point of view or instructional perspective. And that is, let's see if cluster analysis can, let's say, rightly identify the groupings of these variables. So this is very, very helpful from a teaching perspective, a learning perspective, to still apply cluster analysis to a data set like this where we actually already know what the groupings are. But let me emphasize again, when you're outside this class, you typically would not want to use cluster analysis in a situation where you already know what the groups are. Okay? Please be aware of that. So, apply furthest neighbor. So what you're going to do is standardize the data again. Get the distance matrix. Use the h-clus function with the furthest neighbor method, the complete linkage. Then, part A. Tell me, which 2 observations are joined into a cluster first? Well, we looked at the goblet data set, how one can make that determination. So just give you the observation numbers. Part B, tell me what the actual standardized Euclidean distance for these 2 observations are in A. And as a way for me to, or a way for you to show me, show me that you truly understand how this furthest neighbor method does everything. Show me how this distance calculation is completed using actual matrix algebra in R. So get those 2 observations, do the standardized Euclidean distance in R. Actually write out the equations that are being used. So in your Word document, write out the vectors and everything that's actually being done. Part C, construct a hierarchical tree diagram. How many clusters are appropriate for the data? As we saw from the goblet data set, there may be more than one that, at least initially, seem to be reasonable. Give me two choices, the two that you think are most reasonable for this data set. Ignore the fact that we know that there are, I think, 7 different positions. Just ignore that, okay? Part D. For the 2 choices in the previous part, construct parallel coordinates plots with the cluster memberships appropriately identified, just like what we just saw with the goblet data. Plot the original variables themselves rather than the PC scores. Excuse me. Interpret the clusters. Now, something on your own, you should also, not in the project, but just on your own, look at the principal component scores and actually do plots of the principal component scores like what we did. I chose not to include that in this project just to save you time. But in an actual analysis, you would still do those principal component score plots too. So this is problem number 1. Are there any questions? So problem number 2 deals with another clustering method that we're going to be talking about now, called k-means clustering. So there are hierarchical clustering methods. They're called that because, we essentially are forming the clusters in a hierarchy. We are, in terms of the agglomerative methods, we are joining clusters together in a hierarchy until we get to a point where we only have one cluster. Another big categorization of these clustering methods is what's called non-hierarchical clustering. And probably the most popular of these methods inside non-hierarchical clustering is something called k-means clustering, where K corresponds to the number of clusters of interest. One of the things that makes this way of doing cluster analysis different from what we've seen is that you have to actually pre-specify how many clusters you want. And so you can think of it then, well, wait a second, aren't you going to bias, what the end result is? Well, sort of. We'll look at other ways to deal with that issue. But this is an issue that you have to specify how many clusters you want to have at the very beginning for this to work. But so that's a possible problem or disadvantage. Sorry. But here's a possible advantage. So with hierarchical clustering, remember we always had to find that distance matrix, where we had to find all pairwise distances, all distances between pairwise observations. That's okay if we have 100 observations or 1,000. But imagine if you had hundreds of thousands, millions, even billions. Imagine how many distances that you would need to find. For those of you who have a more mathematical background, let's say if I have 1 million observations, how many pairwise observations, how many distances would you need? What would be the value? Use combinatorics. 1 million, choose 2. Okay? That's going to be a really big number. It will take a while to do all those computations. With k-means clustering, you don't need to find all those distances. Yes, you do need to find some distances, but you don't need to find that many. So this is a potential advantage. And therefore, it can be more easily applied to large data sets. So let's look at the process of how this works. It's an iterative process here, okay? First, you need to pick K, the number of clusters you want. And what this K is used is to find, let's say, initial cluster centers. So, we've seen clusters, and basically you need to, think of it in 2 dimensions. You need to figure out, well, where should I put that center of that cluster? And so what happens is that these, let's see now, what typically is done is that you choose K observations at random from your data set. These will be your initial cluster centers, or what people often refer to as seed points, because you're going to grow the cluster around it. So if I have 100 observations, K is 5, I'm going to randomly choose 5 observations from the data set, and that's where I'm going to grow the clusters from. Here's a little bit of a diagram that shows you what's going to happen. So all the plotting points there are actual observations, where let's say K was equal to 3, and I happen to choose this observation, and this observation at random. Note, I should also start off saying you work with your standardized values, and let's say we only have 2 variables to make this easy. Okay, so that's where we're going to grow the clusters from. Step 2, for each observation, assign it to a cluster with the nearest seed. Euclidean distances of standardized variables are typically used here. So as you can see here in terms of my drawing the clusters, I've saw that, for example, this observation here, what I needed to do was find the distance between that observation and that one, and that one. And we can see that the one I just kind of try to highlight in yellow was the closest. So because of that, I'm going to assign that observation to that kind of a purplish cluster. So notice I only needed to find just 3 distances here for that particular observation. Before I would have, with hierarchical clustering, I would have had to find a lot more distances. And so I roughly, obviously I do not have numerical scales for Z1 and Z2. That's okay, it's just a diagram. I've roughly put everything into different clusters. That's step 2. Step 3. Replace those seed points that we originally chose at random with corresponding cluster means. So in other words, so for this like purplish like cluster, I found the mean Z1, I found the mean Z2 for all those 7 observations in that cluster. And let's say that mean ends up being right there. So the mean is Z1, the mean is Z2. For the blue cluster, I did exactly the same thing. Notice how that's kind of in the center of those 2 points. And for the green cluster, I did the same thing as well. Okay. Step 4, we're almost done. Reassign observations to clusters with the nearest cluster mean. So this is part of the iterative process. Now we are reforming clusters. So in this particular case, the difference was this. Before that thing I just circled, before that was in the purple cluster. And I know it's a little bit hard to see, but let's say now the distance between this observation and that cluster mean, the distance between this observation and that cluster mean, let's say that this distance here was smaller. It kind of looks like that. I wasn't perfect when I did this diagram. So because of that, that observation now gets put into a different cluster. Now you can imagine, okay, that cluster mean is going to change, that center point. So what do? Well, I guess I didn't do it there. But what we do now is recalculate. So now the blue mean will somewhere be here. The purple mean will probably be a little bit over here. And we again find the distances between every observation and that cluster mean and the other cluster means. And we look, do I need to make any reassignments again? If I don't, I stop. I'm done. If I do, okay, well then we reassign the observations to a new cluster and we continue going on and on and on. It's an iterative process. This is how k-means clustering works. Any questions?
Where do we start? Like when there are no more iterations required.
Yep.
There's no more iterations of the inside.
Yeah. Yeah.
Those would be the final number of clusters.
Yeah. Yep. So now you might be wondering, okay, well, how do I measure how good a cluster is? How good is this process? And in particular, eventually, as we will get to, what if I would have chose k equal 5 or k equal 10? Would I have gotten better results? And as you might expect, there is a statistic that we can calculate that measures how good we're doing. And it's based upon something that all of you are familiar with already, sums of squares. So, in your first stat, second stat course, you learned about analysis of variance, which involved a number of sums of squares. You learned about regression analysis, which involved sums of squares. Remember a term like sums of squares error, SSE? Essentially, that's what we're going to calculate here as a measurement of how good we're doing. We're running out of time, so we can't really get into it right now, but this is what we're going to calculate to measure how good k equal 3 clusters were. The smaller the number, the better. Okay, so we're running out of time. Are there any questions? So what's next for here today? I have my office hours. Thursday, we will continue with cluster analysis. Maybe we'll get to discriminant analysis. I don't know. We'll see. We will talk some more about project number 2. And then looking further ahead, test number 3 is scheduled for Thursday, December 4th. So that is all then here for today.